For the introduction, and I thank you for the invitation. So I will talk about theta functions and the identities involving theta functions, what we call modular equations. And so these are the classical theta function, var phi of q, phi of psi of q, and we have the eta function. So when you multiply by a suitable power of q, they become almost a quadratic form, a square in a way. So this is almost a representation for triangular numbers. And the eta function is another bilateral infinite series. And if you, so this is, if we set q to be e to the 2 pi I tau, the EQ function becomes the eta function, eta of tau. And so each of these functions are what we call modular forms of weight 1/2. So modular weight of weight k is a meromorphic function that satisfies functional equations like this. So here, AD minus BC is 1, A, B, C, and D are integers. What we call V is called a multiplier. It's a complex number whose magnitude is 1. So K is the weight. In this case, these all have weight 1/2. And if you remember the classical formula, the Dedekind theta function has this transformation property. So we can also look at classical theta functions with arguments, say minus q or q squares or powers of q. They are all going to be modular functions. So each theta function has an infinite product representation, which follows from a general identity due to Jacobi, which we call Jacobi's triple product identity. And the simplest representation is for the eta function, E of q. And for each classical theta function can be written as a quotient using the Dedekind theta function, essentially. So we can do this for var phi of q. We can do this for phi of q. We can do it for theta of minus q. Basically, if I apply the Jacobi triple product identity directly, theta of minus q would be this infinite product here, but you can manipulate these infinite products and write everything in terms of the Dedekind theta function. So, I mean, if you apply the Jacobi directly, you will get a simpler representation, but it will not be necessarily in terms of eta function. Okay. And let me sketch briefly indicate how one can prove identities like this. And my focus is largely on proving theta function identities. So I will give some details, little bit of details. So if you have a function, a complex valued function that satisfies Q difference equations like this, then in any region, avoiding 0, we can say that using the number of poles minus the number of zeros will be k, whether k is negative or positive. So for the function, if I do not denote the right-hand side and the left-hand side of this, the difference of this by a of z, I can easily see that it will satisfy this Q difference equation. And it has no poles, so it says then the conclusion would be that the number of zeros of this function is 1. But basically you can, or this function is constant. You can show that this has more than 1 0. Basically you are gonna substitute here z equals 1 or minus 1. Basically proving this identity in general reduces to, knowing the special cases, 2 special cases of this identity. So if you can prove this identity for 2 different values of z, then you will prove it in general, okay? Another approach would be to realize these things as periodic functions. So let me define theta function using v and tau. So here I set z to be e to the 2 pi I v and v to be e to the pi I tau. And this is, I mean, you can specialize z and q so that this becomes any one of those classical theta functions. So this divided by the infinite product representation, you can see that this function has 2 poles. So this is doubly periodic. And this is algebra, purely algebra, not much here. And you can also see that the zeros of the numerator are canceled by the zeros of the denominator. So this is a periodic function without any poles, so it must be constant. To find that constant, for example, Gauss showed that this constant was 1. So basically this expression as a function of v is a constant called the t of q. Using the theta functions, simple properties of theta function, Gauss shows that c of q equals c of q to the 4. Q here is a complex number less than 1 in absolute value. So you repeat this and you get q to the infinity, which is 1. So c of q equals c of 1, which is 1. So you show that that constant is 1. So basically you can look at these. I mean, you can always, if you look at ratios of theta functions, they will be periodic functions. So proving identities will be a lot easier that way. Okay. So what we call a modular equation of degree n is just a functional relation, just an equation that relates classical theta functions with arguments q and q to the n. So here I have an example of a modular equation of degree 3. This is due to Legendre, I believe. So basically, we have the classical theta functions with argument q or minus q or powers of q, and they are related by theta functions with argument q to the n or minus q to the n or q to the 2n. So the theory started with London. So basically, what we do, we represent theta function. We parameterize them using elliptic integrals, and those integrals. So the transformation properties were studied first by London. Then Legendre and Jacobi came up with the first examples of modular equations. And these are the mathematicians who made contributions to the theory. So I'm familiar with the work of Weber and Schauffele a little bit. So basically what they do, they obtain these special modular equations that allows them to evaluate these elliptic integrals, or they evaluate these theta functions at quadratic irrationals. So this is, for example, a formula which is due to Ramanujan. So using modular equations of degree 5, Ramanujan proves, does this evaluation. So basically you evaluate either, so this is an eta quotient, so you evaluate that eta quotient at argument e to the minus pi. Now, so the elliptic integrals here are defined this way. So if we define z to be the elliptic integral of the second kind, and if we define q to be the ratios of these elliptic integrals, this here is alpha is the alpha and minus alpha are called the modulus, and so 1 minus alpha is called, I forgot what it's called. So now if we define z and q this way, then we can basically show that phi of q is the square of this elliptic integral, square of z. And theta of minus q is square of that elliptic integral multiplied by 1 minus alpha to the 1/4. Basically, you are parameterizing theta functions using elliptic integrals, okay? And the modulus of that elliptic integral. Now, the proof of this is not that deep, but it is quite lengthy. So basically what you do, you use properties of theta functions, simple properties of theta functions, basically the function var phi of q, and basically you do here change of variables in this integral. So it follows from a series of transformation formulas. Once you have this representation for var phi of q and var phi of minus q, then you can basically use theta function identities and to get representation for other classical theta functions. So now this is a theta function identity. Improving identities like this, these are not difficult to prove actually, but basically improving identities like this, you are using the additive properties of these things. Okay, so this is a classical theta function identity, which is due to Jacobi. So using this theta function identity, you can express phi of psi of q square in terms of z and alpha. Now, here, if I want to express var phi of q, then I'm going to use this. This is a trivial identity. This now follows from the infinite product representation of these functions. Basically, each of them is an infinite product. Each of them can be written in terms of the eta function, and you can clearly, easily justify this. So now you can have a representation for var phi of q. Basically, you can have a representation, you can express any classical theta function in terms of z and the modulus alpha and 1 minus alpha. And so we set if n is an odd integer, we denote this by root zn. And this becomes root zn 1 minus beta to the 1/4. Basically, alpha corresponds to q, beta corresponds to q to the n, z1 corresponds to q, zn corresponds to q to the n. Okay, so if you do this, if you use this parameterization, then the example that I gave, that modular equations of degree 3 takes this simpler form. So if you put all these parameterizations, and there will be lots of cancellation. Usually this, the z cancels out. Usually the equations only involves alpha and beta. So you get this, this equation involving alpha, beta, 1 minus alpha and 1 minus beta. Okay, so let me give you others examples of modular equations. So these are modular equations of degree 7. Now, you can see the similarity between the second and the third one. These are actually equivalent to each other. If you look at things as, as an equation involving modular functions, then you basically do the transformation tau goes to minus 1/7 tau. So these two are actually equivalent to each other under that transformation, but there is actually a simpler way of doing this using modular equations. And if you replace alpha by 1 minus beta, beta by 1 minus alpha, z1/z7 by 7 times z7/z1, you can go from a modular equation to another modular equation. Basically here, 1 minus beta goes to alpha, beta goes to 1 minus alpha, alpha goes to 1 minus beta, 1 minus alpha goes to beta. This goes to 7 times z7/z1. Okay, so these two are also equivalent using that transformation, this transformation here. There are several different transformation properties like this. Basically, let me not get into those, okay? So let me give you a sketch of how to obtain a modular equations of degree 61. So Ramanujan, so basically the focus is on modular functions. So nowadays people work with modular functions. They use modular properties of these functions. The classical theory is not left behind pretty much. It was the case, and then Ramanujan came and he gave a large list of modular equations. And probably he gave more modular equation than what have been proven so far. So, so to prove his modular equations, general theta function identities were devised. And this is an identity like that. Basically, this is an identity due to L.J. Rogers. Basically, what we have here is a restricted quadratic form. So here T is this quadratic form. We have these extra variables, and we have this sign alterations. So we have lots of variables here. Basically, this capital U and capital V defined this way. So we also have these parity restrictions. So in the simplest case of Rogers, there were no parity restrictions and there were no sign alterations. Then Brisou did some work. Then we introduced these extra variables, and we also, so T and L gives you the parity restrictions, but T and L doesn't have to be an integer actually. So this doesn't have to be a quadratic form. So in this, in the generalization that we give, we have these free variables, all possible sign alterations, and all possible quadratic forms with all restrictions. So you start with a quadratic form like this. Here we have many variables. The main variables are alpha, beta, m, p, and this is not alpha, this is lambda. So basically you have alpha, beta, m, p, and lambda. You want them to satisfy this equation. And if you think of this as a quadratic form, and if you look at the discriminant, you see that the discriminant is minus alpha, beta. So what we do with this restricted quadratic form, we first diagonalize this. So we write this as a product of theta functions, sum of product of theta functions. So that's the first aim. Then what you do, you make a change of variables here. Basically, the change of variables that you make here are trivial, but they correspond to a non-trivial representation in terms of theta functions. So you write this as sum of product of theta functions, and the trivial change of variables that you make in this sum corresponds to non-trivial representation in terms of product of theta functions. So basically, again, the discriminant here is minus alpha, beta, and if you can find alpha 1, beta 1, m1, and p1 satisfying this equation. Also, alpha beta equals minus alpha 1, beta 1, and this here is an integer. Then basically here we make a simple change of variables here without changing the discriminant. So basically you have an equivalent quadratic form here. So basically alpha goes to alpha 1, beta goes to beta 1, m goes to m1, p goes to p1, lambda is fixed. All those variables x, y are changed suitably. These lambda, epsilon, delta, they change suitably. So basically you have this, of course, I mean the quadratic form does not change, but the representation in terms of theta function changes. So now I need to define the general theta function. The general theta function, this is the notation of Ramanujan. So the the theta function phi of q in this notation takes this form. Psi of q is this, E of q is this, okay? Now, so basically when you apply this formula here, as I said, this is gonna be a sum of product of theta functions where the P and alpha here, the weight of these theta functions will be P and alpha. By weight, I mean this. For example, this is weight, this function has weight Q squared, this function has weight Q to the 4, Q times Q cubed, this function has weight Q cubed. If the weight is 2 or 4, or say 3, the functions that show up, the theta functions that show up will be classical theta functions. If the weight is 8, you can still write them in terms of classical theta functions. Basically, if the weight is a power of 2, you can somehow write them using classical theta functions. So for example, if I take my alpha to be, if I take my alpha to be 3 and beta to be 61, m to be 1, this is gonna be 64. So this is 8 times 8. So all those functions will be classical theta functions, but unfortunately, they will involve cubes because of alpha. So basically they will, you will get the theta function identity like this. So you will have sums of product of theta functions, but they will involve the arguments cube and q to the 61. So this is not going to be a modular equation of 61 because of that cubes. These are called mixed modules. So this is a mixed modular, this is a composite modular equation with degree 361. Okay, so now somehow we want to get rid of this cubes here, okay? So to do that, we choose the parameters in such a way that when we write these things as sums of product of theta functions, we combine terms that have this weight 3 into theta functions that has weight 1. So basically this is what is called the quintuple product identity. It's an important theta function identity. So basically you can combine this sum into a simple single product, and you can, basically you have weight 3 here, weight 3 here, and you have weight 1, weight 1. So basically I want to set my parameters here. Basically I take this T and L are no longer integers. Basically, I take T to be 1/3, L to be 2/3. So you actually make use of the fact that these are not integers, and so that I have these terms that appear in my expansion, I can combine them into a single product, so I can basically get rid of cubes. And what is left with will be only an equation that involves Q and Q to the 61. So this is what we get. So we get, for simplicity, I'm gonna put A to be Q to the 61. With A is Q to the 61, and C of Q squared is defined this way. This is the theta function identity I get. This is the eta quotient multiplied by this at minus Q minus the eta quotient multiply this thing at Q equals this thing at minus Q to the 4, this at Q to the 4. Again, A is Q to the 61 for simplicity, plus these two terms as well. Okay, actually, now the reason that we get is basically C of Q. If I were to write down C of Q, I would get square roots here. The reason that I get square roots like this, because basically the functions that shows up, let me see what they are. I did not put them, but they show up in the odd even expansion of psi of Q. So you can write everything in terms of psi of Q, but you need to use square roots. So anyway, so you can actually, you can get rid of square roots by taking square of this expression here and use some theta function identities. Now, when you write these in terms of, if you use the parameterization z, 1 minus alpha, 1 minus beta, the representation that you get here won't be pretty because of these high powers of 2. So you have, you know, this is 61 multiplied by 32 minus q to the 8 here, q to the 8 here, 61 times 8 here. Basically, when you try to write these in terms of with arguments q or q square, you have these nested squares. So basically, for example, to be able to simplify this expression here, I need to look at the 6th power of this term and this term. The reason that I look at the 6th power because of this, and when I try to express e to the q to the 32 in terms of smaller arguments, I need to use this, you know, theta function identities. These are trivial identities, but basically when you do this, you will have these nested roots. When you go down the argument from 32 to 2, you will have these nested roots. Basically, so after some manipulation and algebra, you can see that this here, this expression, this one here, reduces to this. So this expression here to the 1 over 6th power multiplied by this square root here. Now, if I use that parameterization, this thing here will be simple, this thing here will be simple, this here will be simple, so this here will be simple, but these again, I need to use nested roots because they don't have, you know, representations in terms of alpha and z. I mean, they will have after I reduce this to 2. So I need to go down all the way down to 2. So I could write down the modular equation, but it is ugly at this stage. I'm working on this, try to simplify it, try to write it in a readable form. So somehow, I mean, I can write these, I can get these simple, I mean, this is quite simple. This is not bad, but the constant that I get in front does not agree from what I would get from this one here. So I cannot factor out those constants and cancel. So as a theta function identity, it is not bad. Usually when you transform a theta function identity to a modular equation, it takes a simpler form. But in this case, because of these high powers of 2, the representation is not pretty. And so best of my knowledge, Ramanujan does not have a modular equation of degree 61. And I did not see one listed by Weber or Scheffler or others. So you can also search for these identities using computer algebra system. And there are actually algorithms that does that, computer algebra packages I know one by Frank Garvan. You can search for identities like this, and you can also verify identities. Once an identity is given, you can verify that identity using the theory of modular forms. The modular forms are like, modular functions are like polynomials. They cannot have too many zeros. So basically, if you look at this as a, if you expand each term here, the Q expansion, you will see that everything will cancel out. So that means this thing will have too many zeros, and this being a modular function cannot have too many zeros, so it must be constant 0. So there are computer algebra packages that will do that for you. You simply give the equation, you write everything in terms of eta functions or classical theta functions, and that will justify the identity for you. You can also search for identities like this, but as the degree gets large, the computation gets challenging, because basically you cannot get a linear relation. You need to have a nonlinear relation because of these high powers of 2 here. either you are going to put lots of functions there, then the search will be time consuming. If you want to get an identity involving only small powers of Q, then it will have a very large degree and it will be nonlinear. So that will be computationally difficult as well. So of course, when you have a general identity, you can get many identities like this, not just one. So the beauty with the theta function identities is that you don't get a single identity, you get many identities like this. And the theta function identities are quite useful for manipulations in very simple forms, like take this Jacobi triple product identity. This is a very simple theta function identity here. Here, even if you you can do a like find a zero here, divide by that, take limit. One can start with this and get a formula for number of representation by squares, for example. So these are very open to manipulation. You can like take limits, basically find a zero here. I need to make a change of variables here. For example, to make this expression 0, then divide by that, use L'Hopital rule, So you can actually differentiate here using logarithmic differentiation. You can get, even the simpler identity will give you, say, the representation by sums of 2 squares. The more general identity will give the stronger results. For example, we have an identity like this, which is called 8 psi 8. Basically, the special cases of that identity gives you formulas for sums of 8 squares, sums of 4 squares, and such. Okay, so I mean, the general theta function identities are quite very good to manipulate. So you can manipulate them, and you can get interesting results. Okay. So this is I don't know. Let me go back to. So this is again due to the initial case of this formula was due to L.J. Rogers. Then David Bressoud in his PhD thesis worked with a slight generalization of this and to prove some identities due to Ramanujan. I gave another generalization and used it again to prove some identities of Ramanujan as well. And then later we realized that we could actually use this also to get modular equations. And so basically you can do this with 161, you can do it with so that for some modulus this will work. But I found that only 61 is missing in the literature. Other moduli, they have identities, modular equation for that given degree, but for 61, I could not find any modular equation. So I had no questions, so I always go fast and I'm done.
Hey, thank you very much, Hamza, for your very nice talk.
Welcome.
The members of the audience can please unmute their mics so that we can all thank Hamza for his nice talk. The members of the audience, if you have any questions, please ask.
I should say that this is also related to class field theory, and the reason that Weber was studying these functions, these equations, modular equations, because he wanted to evaluate these invariants. He could then go back and find the Hilbert class fields of some numbers. So that, I mean, that was his motivation. So I mean, this is related to a lot of many areas of mathematics. These things. Basically, there are very general formulas where you have the Dedekind theta function evaluated at an quadratic irrational number equals, product of gamma functions at certain arguments. So there is a bit of research over there, to evaluate those, to get those explicit evaluations, and Selberg-Chawla formula, basically, that's what's called. So this is, but my focus is on not those, my focus is on basically on theta function identities, general theta function identities. That's what I'm studying mostly.
If there are any questions, please ask. And if there are no questions, then thank you very much again, Hamza, for your very nice talk. And thank you everyone for coming. And so our next session will be in 2 weeks, same time. So we'll see you in 2 weeks. Bye, everyone.
Bye.